So now that we've kind of looked at the various ways in which we can evaluate different limits, whether through direct substitution or kind of through approximations or limits at infinity, it's time we kind of start shifting now and looking at these different theorems that exist as a result of, limits. And so one of the most important theorems, in my opinion, is the squeeze theorem, or it's also referred to as the sandwich theorem, although I think that kind of sounds quite silly. And the squeeze theorem, it's a bit kind of convoluted at first, but I'm going to give you like kind of two examples that will really help illustrate it and how you can use it in order to evaluate limits that may be a little bit more intense to evaluate otherwise. And so the squeeze theorem tells us that suppose we have a function f of x, which is kind of, a way you can think about it is kind of like bounded by two functions, by g of x and h of x, such that, f of x is greater than or equal to g of x, however less than or equal to h of x, such that the following property holds true, that the limit as x approaches a of g of x is equal to the limit as x approaches a of h of x, and we're going to call this some value L, and of course this value L has to kind of exist. I mean, it could be an infinite value, however, as long as it kind of exists. Then we can say that the limit as x approaches a of f of x is going to be equal to L, assuming that these two conditions over here hold true. This is a bit convoluted, but I'm going to give you one example that I constructed over here that will kind of help you, I guess you can say, kind of understand this in a more concrete manner. So suppose we have the function x over sine of x, and actually in a previous video I accidentally said that this function is sine of x over x. However, I couldn't really bother to correct that, so I'll be correcting it right now. But essentially, we have the function x over sine of x. Over here, it's actually written in this sort of magenta color. Let me write y equals x over sine of x. And we want to take the limit as x approaches 0. We've actually worked with this example. We've worked with the reciprocal, but we're going to end up with the same answer, you'll come to find. And so essentially, I graphed that out over here. At least I graphed a portion of it, and you can't really see it, but there is a removable discontinuity right over here at this point. At x equals 0. And so if we were to use direct substitution, then here we would get 0 over sine of 0, which is just 0 over 0, and that doesn't necessarily work out. And so what we can do is we can find two functions, and I just, arbitrarily selected these two functions. I found, y equals 10x squared plus 1 and y equals negative 10x squared plus 1. And, I mean, just, based on their graphs, you can tell that x over sine of x is going to be bounded by these two functions because, this initial property over here holds true for these two functions. And so we can take the limit as x approaches 0. I'm not really going to stick to the color coding of 10x squared plus 1. And I mean, we can just use direct substitution because it's a continuous function, so we'll just get 1. And then we can take the limit as x approaches 0 of negative 10x squared plus 1. And again, by direct substitution, we'll get 1. So these two right over here, these two are equal to each other. And so because of the fact that these two are equal to each other and that x over sine of x is kind of bound by these two functions, we can then say that this limit over here is going to be equal to 1. And so you can't really use direct substitution. We will learn another method later on when we get into differential calculus that is something that you're going to eventually end up relying on for your IB or AP exams. However, for the time being, the squeeze theorem is a pretty helpful way. If you're given two functions, or if you know that, this particular function over here is bounded by some functions and you have this property holding true for the two functions that you can select, then you can use the squeeze theorem. Now, the proof of the squeeze theorem is a little bit intense and definitely outside of the scope of Calculus 1. However, for the time being, we'll just accept the fact that it does actually work. And if you do graph out this function, you will find that this point over here is 0, 1. And now, I found this other example over here that's a little bit more intense, and this is actually from the UC Davis math department, so very large thank you to them. I just found this question set online, to be honest. Because it's quite difficult to construct very advanced questions for the squeeze theorem. But we're taking the limit as x approaches negative infinity of this very intense rational function, and really the only problem here is the sine of 3x, because we know that sine of x diverges as x approaches infinity or negative infinity, because we don't necessarily know whether or not it's going to be negative 1 or somewhere in between, because we know the general property that sine of x, or in particular we could say sine of 3x, is going to be bounded by 1 and negative 1, right? And so what we can do, the way we can actually approach this is we can kind of construct this function over here, and I'm actually going to go ahead and switch colors. We can construct this function over here using this piece of information. So let's see how we can do that. We know that sine of 3x is going to be bounded by 1 and negative 1, so we can just multiply everything by negative 1, and we'll get negative 1 is less than or equal to negative sine of 3x, which is less than or equal to 1. And then we can go ahead and add 5x squared to both sides, so we'll get 5x squared. Let me actually do this on another line. 5x squared minus 1 is less than or equal to 5x squared minus sine of 3x, which is going to be less than or equal to 5x squared plus 1. So as you can see, we're kind of just using this first piece of information, and we're building up our rational function using that simple piece of information. And then finally, we can divide everything by x squared plus 10. So I'm just going to go ahead and do that. So we'll get x squared plus 10. And then here we'll get x squared plus 10 in the denominator for all of these terms. Okay, so it seems that we have two functions over here that, our initial crazy rational expression was bound by. And so what we can do now is we can try to see if our initial condition, if our first condition of kind of having these two limits being equivalent actually holds. So let's go ahead and try that out. I'm going to again arbitrarily switch colors. This is a nice pink color. The limit as x approaches negative infinity of 5x squared minus 1 over x squared plus 10. If we go back to when we were looking at limits at infinity, we can kind of look at the dominating term, and so we'll see we have 5x squared over x squared. These two terms can cancel out, and so this limit is going to be equal to 5. And then we can go ahead and do the same exact thing for our other function, for kind of like our upper bound function, if you will. And so we will find the exact same solution as well, because the dominating term here is the x squared term and the 5x squared term. So we will get 5x squared over x squared, because we can just ignore the negative 1 and the 10, or the positive 1 and the 10 in this case, and then we'll just be left with 5. So we see, again, these two limits, these are equal to each other, and so now we know that since our rational expression is bounded by these two functions and their limits are equal to each other, we can thus say by the squeeze theorem that this limit over here is in fact going to be equal to 5. And so that's a very interesting thing. It would be very difficult to kind of try to solve this using our basic principles of limits at infinity, because, we don't really know what happens to sine of x as x approaches plus or minus infinity, because it's going to be bounded somewhere between negative 1 and 1. And just using this piece of information, we were able to construct, or at least locate, two functions and, that our initial rational function was bound above and bound below by. And then we were able to use our knowledge of limits at infinity to kind of evaluate these limits, which were significantly easier than this one over here. And so we were able to evaluate these limits at infinity. We found that they were equal to each other, and then we could use the squeeze theorem to officially make the statement that this limit as x approaches negative infinity is equal to 5.